Hello, Mr. Claudy here. And after finishing a section on arithmetic series, you guessed it, we're going to continue by looking at the geometric series. Now, geometric series is just the sum of all the terms of a geometric sequence. The formula, I am just going to give you the formula. I don't necessarily like doing that, but there is a proof out there. It's in your textbook. It's not a terrible proof, so if you really want to see proof, you can take a look at that. But this section, more than all the other ones, you do kind of get into a habit of just relying on the formula. So we have the sum of a geometric series. It's written with this formula. You have the first term times the common ratio of the power of n, the number of terms, minus 1 over r minus 1. And r cannot equal 1. You'd have a problem then, right? You'd have a denominator equal to 0. Okay. So let's start with an easy example. This is a story, actually. So according to legend, Sisa ibn Dahir invented the game of chess for King Shihram, who was a tyrant ruler in India over 1,000 years ago. Now the king liked the game so much that he offered Sisa ibn Dahir a reward. Now the inventor, this guy thought about it for a second. He said, okay, well, I would like 1 grain of wheat for the first square on the chessboard, 2 grains for the second square, 4 grains for the third square, and so on. So each square, I want to double the number of wheat grains that I receive. And there, remember, this is a chessboard, so there are 8 times 8 squares, so 64 squares. The king was like, oh, this sounds like nothing. And he's like, for sure, I'll pay you that wheat. So the question is, how many grains of wheat did the king have to pay? So in this example, the sum that I'm trying to figure out is, okay, the first square had 1, the second square had 2, the third square had 4, and it keeps doubling every time. So the next square is going to be 8, 16, plus dot, dot, dot. Now, what type of sequences or series is this? Well, here I multiplied the answer by 2, here I multiplied it by 2, so I actually have a common ratio. This is a geometric series. So I'm going to rely on this formula, and let's write out, do I know any of the terms? Well, I know u1 is equal to the first term, that's 1. I know that the number of squares in this case was 64, and the common ratio, we just figured it out, was 2. So then I'm going to use the formula S sub n is equal to, let's write it out the first time here. So I have 1 times 2 to the power of 64 minus 1 over 2 minus 1. So we end up with 2 to the 64 minus 1. It's a big number. Let me type it into my calculator just to see what it is. 2 to the power of 64. Whoa, minus 1, of course, don't forget that. So the answer is 1.8447 times 10 to the 19. Now, if you recall this sort of standard notation, this is a humongous number. This is 1.8446744407. That's all of the decimals on my calculator. It should be 19 decimals, right? This is times 10 to the 19, so it's times, I have to move the decimal place over 19 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So, which is crazy, right? But it's the doubling. And I mean, King Shihram obviously didn't have the formula for geometric series. He wouldn't have agreed to this ridiculous price, but he also doesn't have an understanding of exponential growth. Remember, geometric sequence, geometric series is rooted in exponential growth. And even though you start with 1 and it's doubling, the doubling speeds up very quickly in a way that's hard for a human to understand. The king was disappointed to learn, and this is how the legend ends, that this was more grain than exists in the entire world. So hopefully if you're ever in a high stakes situation where you need to pay someone grains of wheat on a chessboard, you just remember The Folly of King Shahram. Okay, let's do another question, a more difficult question. So I have a geometric series. It's got some of those fractions. Well, let's just try to figure out we know it's geometric, so let's try to figure out the common ratio. Now remember, if you get confused, you take the term and divide it by the previous term. Now, division of fractions is just multiplication by the reciprocal. These 5's cancel out, so I end up with 4 over 8, which is just half. And if you look at these, every time I'm just multiplying the denominator by 2. So you can actually, we kind of have figured out the R value. Okay, so the question then is to find the sum of this series. Okay, well, how many terms are there? Or sorry, the first term, that is 5 over 4. Okay, that's easy enough. And the number of terms. I don't know what the number of terms is, right? That's a problem. Don't know that. And the common ratio is half. So I have a problem here in that I don't know how many terms there are. Now this is kind of familiar. We've had a question in this chapter already with this. So I need to figure out which term number is 5 over 256. To do that, I'm going to sub into the geometric sequence formula. So I have, if you don't remember that, that's un is equal to u sub 1 times r to the power of n minus 1. Let me sub in some values here. So I know u sub n is equal to 5 over 256. U1 is 5 over 4. R is half. And this is to the power of n minus 1. So now I need to solve. Okay, so let's see if I can solve for n here. Not so bad. I mean, first I want to get rid of the 5 over 4, so I'm going to multiply by 4 over 5, both sides. These cancel out, and 256 divided by 4 gives me 64. So I end up with 1 over 64 is equal to 1 over 2 to the power of n minus 1. Okay, so now you have 1 over 64 is equal to half the power of n minus 1. I like this question doing it a little bit by hand because it reminds you, like, do you remember how to solve a question like this? This is an exponential question, but 64 and 2 are related, right? I should be able to make this so that the bases are the same. 1 over 2 to the power of what gives me 64? Well, 2 times 1 is 2, 4, 8, 16, 32. So this is to the power of 6. And this is half to the power of n minus 1. So then I can use equivalent, because the bases are the same, I can set the exponents equal, and I end up with n equals 7. So hopefully you remember doing that. That's from the exponential chapter. Okay, but the point of this was to find out what n was. So now I know n equals 7. So now I can use the formula for sum. Sn is equal to u1 r to the power of n minus 1 over r minus 1. I have u sub 1, which is 5 over 4, r to the power of n, which is half to the power of 7 minus 1 over 7 minus 1. Oops, sorry, half minus 1. Okay, and I'm going to type that into my calculator. So 0.5 to the power of 7 minus 1 times 5 over 4 divided by negative 0.5. And that gives me 2.48. I'm not going to, again, you probably could have done it by hand. I didn't feel like it, to be honest, but you could have done it by hand as well. And you'll notice this is a small number. So it's not necessarily true that all geometric series add up to a humongous number. And if you look at this, part of the reason why, and this is getting us ready for tomorrow's lesson, is the numbers aren't actually getting bigger. Because the R value is less than 1, and we talked about this a little bit before, it means that actually each term is smaller than the last. I mean, 5 out of 256 is a tiny amount of pizza compared to 5 out of 8 pizza, or even 5 out of 4. So these terms are getting smaller and smaller. So actually the sum is not going to be this huge number. You could have solved this using by hand using the fractions, but you basically are getting a small number. Sometimes you see the sequence or the series formula written backwards, like where the negatives have been factored out of the numerator and denominator. It gives you the same answer, so that's fine. Let's turn a la page and do one more. We'll call it the difficult example, hard example. How many terms of this series are needed to exceed a sum of 35? So there's a lot to figure out there, a lot to digest. But basically, first of all, looking at this series, okay, maybe it's arithmetic. I subtract 0.4, but then I don't subtract 0.4 here. So it's clearly not arithmetic. Let me try finding a common ratio. So that means I take my final number, or my term, and I divide it by my previous term. And I get 3.6 divided by 4, which is 0.9. Does that check out? What about over here? 0.9 as well. So I can state confidently that this is a geometric series. I'm very excited because now I can use my formula. The common ratio is equal to 0.9. We figured that out. My first term is equal to 4, and the number of terms unknown. Actually, we were given some more information. We want to find out how many terms give me a sum greater than 35. So we want to have, if we write out this formula, so we want to find when will this exceed 35. So to do that, I'm going to say, okay, 35. I want this thing on the right to be bigger than 35. So I want to have, and then u1 is 4, r to the power of n, 0.9 to the power of n minus 1 over 0.9 minus 1. Ugh, that looks terrible. And it's not going to be great because it's an exponent I have to solve, and it's an inequality. But hopefully you've had a bit of practice in some of the difficult problems we've done in this chapter. So first thing I'm going to do is multiply both sides by 4. Oops. Multiply by 1 over 4. So that gives me, you know what, let's just leave it like this for now. And I end up with 0.9 to the power of n minus 1 over, and I could simplify this, this is going to be negative 0.1. Now, to get rid of this side, I'm going to get rid of the negative 0.1, I'm going to multiply both sides by negative 0.1. But here's the problem. If you multiply or divide an inequality by a negative number, then you have to change the sign. So at this point, I'm going to get 35 divided by 4 times 0.1, and that gives me 0.875, sorry, that's negative. But then this switches sides, and now I have 0.9 to the power of n minus 1. Got to bring that to the other side, so I get negative 0.875 plus 1. That gives me 0.125 is greater than 0.9n. Now I know what you're thinking. Oh, I know what to do here, sir. I just log both sides. And you're right. Then you end up with log 0.125 is greater than, the nice thing about logging both sides is the n can come down. That's using one of your log laws. However, now you might say, oh, I'm just going to divide both sides by log 0.9. Remember, log 0.9 is just a number. You go up to the top of the school, you say, what's log 0.9? And someone else yells back at you, it's negative 0.04575. Problem is, if you divide both sides by a negative, you have to switch the sides again. So what I often recommend, especially in inequalities like this, if you have a tendency to get confused, maybe it's best to turn the numbers into decimals, just so that you don't accidentally forget to switch the signs. And really, any log that's less than 1 is going to be negative. So I have negative 0.045757. Okay, so now when I divide both sides by that amount, I switch the sides again, so now I have n is on this side, and I end up with log 0.125 divided by that answer of mine, which gives me 19.736. Now, what was the question asking? How many terms in the series will give me sum of greater than 35? Well, 19.7 terms will give me exactly 35. If you want more than 35, if you want to exceed 35, you have to actually round up. So therefore, n equals 20 terms. So again, some of this chapter might be review, but there's a lot of concept, or you've done it before, but there's a lot of concepts here that from previously in the course that we're reviewing. Logs to solve an equation, inequalities, and some basic algebra skills. Your homework for tonight then is page 176, number 1 to 3, and page 178, number 1 to 6. I think you should do all of them just to get some more practice in. Good luck with that, and we'll see you next time.